The existence of a supercontinent was conceived by Alfred Wegener in 1915. Wegener hypothesized that over the past 200 million years, the continents had drifted from the supercontinent, Pangaea, to their current positions. The process, called continental drift, was greatly debated from 1924, when Wegener's book, The Origin of Continents and Oceans, was translated into English. Of the many arguments to reject Wegener's theories, lack of explanation on how the continents actually moved was one most agreed on. Following World War II, new equipment and funding was available to research our oceans. As oceanographers began to explore our seafloor, the theory of plate tectonics was born. Researchers eventually discovered that the Earth has 7 major segments, called lithospheric plates. These plates make up 94% of the Earth's surface. The names of the 7 plates, which you will recognize, are the North American, South American, Pacific, African, Eurasian, Australian Indian, and Antarctic plates. The Pacific plate is the largest plate of the 7, which is located in the Pacific Basin. There are 3 types of boundaries that occur between plates: divergent, convergent, and transform boundaries. These boundary types are depicted in the image, with red lines representing divergent plate boundaries, the blue line representing convergent plate boundaries, and the green line representing transform plate boundaries. Divergent plate boundaries, which help to form oceanic ridges, are considered the building site of plate margins. New material rises from the asthenosphere, spreading the seafloor. These boundaries are what continue to move our continents further apart. Convergent plate boundaries are almost completely opposite of divergent boundaries. As 2 plates collide into each other, a convergent boundary is formed. In most cases, the oceanic crust subducts, or slides below the continental crust. The constant pressure helps form mountainous regions along the border. Transform plate boundaries occur when 2 plates slide past one another. In this case, the lithosphere is neither produced nor destroyed. The plates simply slide past one another. Most of the world's transform plates are found on the ocean floor, where offset segments create a step-like plate margin. You might be wondering how the movement of these plates is measured. Stay tuned to find out. There are 2 primary ways in which plate movement is measured: geologic measurement, and measuring plate motion from space. Using geologic measurement to determine plate motion is done by obtaining drilling samples of the ocean floor, determining their age, and using the distance between samples to determine how far a plate has moved in the given period of time. Researchers have obtained hundreds of samples and use this information, along with magnetic information stored in hardened lavas, to create seafloor maps that show the age of the ocean floor. GPS technology is used to measure plate movement from space by placing special equipment in a fixed location for a long period of time. Geologists can obtain the speed at which different plates are moving. This data shows that Hawaii is moving toward Japan at a rate of 8.3 centimeters a year. A location in Maryland is moving away from England at a speed of 1.7 centimeters a year. The map here shows the direction of travel and speed of various plates throughout the world. What actually drives plate motion is a process called convection. Convection is a type of heat transfer that causes movement of a substance. Here you can see as heat is applied to the bottom of the cooking pot, the water expands and becomes more buoyant. This causes the more dense, cooler water to begin to sink. Earth and its plates function in the same manner. When the velocity of the asthenosphere exceeds that of the overlying plate, motion is enhanced by convection. As new material rises to the surface, the plates are driven apart at the mid-oceanic ridge. As the slab reaches a convergent boundary, it has become much cooler, and thus more dense, and begins to sink back into the asthenosphere. The sinking of the cold dense slab is a major factor in plate motion. The whole mantle model shown here demonstrates the sinking of cold oceanic lithosphere. This represents the downward portion of the convection cycle. The upward portion is driven by rising mantle plumes, which carry hot material from the Earth's core toward the surface. In conclusion, Alfred Wegener's hypothesis of a supercontinent, he called Pangaea, paved the way for the ideas we have come to know as fact. What was once thought of as absurd by many in the scientific community was proven to be quite accurate once proper research and funding was available following World War II. Our 7 major plates form 3 distinct boundaries: divergent, convergent, and transform. We can measure movements of these plates, caused by convection, either geologically, or with the aid of GPS technology. The ideas and concepts discussed in this video are taken from the text, Earth, an introduction to physical geology. Many of the wonderful images seen in this video can be found in Chapter 2 of the text. A special thanks to Natural Reader for providing the necessary software to convert text to speech. Yes, all the narration in this video was created through use of this wonderful technology. Check out naturalreaders.com for more information. My daughter Katie insisted I give her a shout out, so here's to you, Katie. You make my world quite interesting.